Hello, in this video, in this session, we will try to look at the next test, which we can use to determine whether the series is convergent or divergent. And the name of the test is called comparison test. Before we start talking about this, let's quickly just to double check that we are okay with the P-series test, which we remember it's based on the integral test. Yeah? And the test is telling us that when we have the infinite series, that form, that formula, the summation from 1 to infinity, 1 over n to the power of p. Yeah? Of course, it reminds us the improper integral. Yeah, I will always refer to that section, but 1 over n to the power of p, only that form. Then we can focus on that p value, and through the integration, we may prove it that if p is greater than 1, the infinite series will be convergent. If it's less than or equal to 1, it's divergent. Of course, the equal one is 1 over n. We know this. This is divergent series and it's called harmonic. Okay, harmonic series. We know this one definitely. We will call this as a P-series test, but to be more like exact, explicit, this is the integral test. Integral test, but to be more efficient, to speed up the process of convergence, divergence, we may use this property. But you may always take this formula, convert to the function, and because this is positive, is continuous, decreasing, integrate, using, of course, the improper integral, and you will get your answer. But that's definitely the conclusion. Okay, that's mean P-series test we will apply a lot. Okay, so now let's look at this comparison test. Next test. What we will do, as the name is suggesting, we will try to compare the given series, the given unknown series, to something that is known. Okay, and this will lead to the extra step that we have to find one additional series that we can compare our unknown, okay, and then making the proper conclusion of the comparison. Let's see. For instance, when we will consider this infinite series, 1 over 2 to the n plus 1, summation from 1 to infinity. Yeah? You may notice, oh, it looks almost like the geometric series because n is placed in the exponent, 1 over 2 to the n. However, that plus 1 is, it's not helpful. That means this reminds us the series of 1 over 2 to the n. Yeah? It's definitely geometric with the first term 1/2, common ratio 1/2, and the sum is 1. Yeah? Quickly, we know I did use that property. That's that formula. Okay, so that's really helpful, convergent. And also when we practicing, you may probably know that addition of 1 is not really making a big difference. Yeah, in this must be convergent. But let's look. We can take our new formula, okay, and compare. I will just take the fraction at the moment. So this is my unknown, that's my formula, unknown, and this is a known, 1 over 2 to the n. That's what I will do. And this is important, the inequality, the relation. The fractions on both sides looks almost identical. However, plus 1, adding 1, we making denominator greater, then the entire fraction is smaller. If the denominator is greater, the whole fraction is smaller. Okay, so we have the relation. And now I can also say for the same number of terms, this relation is true. The summation of this and the summation of these terms, but of course for the same number of terms. okay? And now this one, we figure out that is convergent. This is infinite series convergent. And also, again, I know that I always refer to the improper integral. Oh, we also talked a little bit about comparing the stuff. That means this is convergent, because not always the comparison tool will work. But let's look at this situation. If that sum is convergent, okay, which it's like a finite number, it's actually, even we can see it's convergent to 1. Yeah, everything what is smaller, yeah, that sum for infinitely many terms will be smaller. A number smaller than the finite number must be a finite number. That we will say, okay, we will make this conclusion that this infinite series is convergent by, and we will say direct comparison test, because we directly comparing, okay? Directly comparing. It's convergent by the direct comparison test, and we comparing with this formula. We always have to say what formula we're using, okay? And that's actually the test. But you can see we have to find out the new known formula to compare with. Okay, and this is the same thing. It's less than a finite number. It must be convergent. Important thing, we may use comparison test only when the terms of that sequence of the formula are positive. Because if they are negative or alternating, then we can mess up the relation, the inequality. It will not hold. Okay, that means if the terms are positive, we may use the comparison test. And let's look at the summary of this test. Suppose that the infinite series A sub n and B sub n are the series with the positive terms. Yeah, the same like the integral test is also for the positive terms. Then if the B sub n is usually the new one that we will find out, and we will compare our not known one. B sub n is convergent, and that's the relation. Yeah? Our formula is not known, and it's smaller than this one for all of the n. Then we may conclude that it is convergent because the summation is smaller than the finite number. We may also use the divergent, we may also use the comparison for this scenario. If the infinite series B sub n is divergent, okay, let me say this. If B sub n is divergent, yeah, and our summation, yeah, are actually greater. Yeah. I mean, if this is divergent, yeah, we will find out that something to compare, that's this, is divergent, is known. Then it happens that the relation is this way, that's the relation. Then we may also claim divergence of this infinite series, because everything what is bigger, let's pretend this is like infinity, huge, everything greater beyond the infinity is infinity divergent. Right? So I mean, that's the only case that we can claim divergence or convergence. If the relation is not working, then we will not use it. Yeah, we can see it's not possible. If the terms are larger than the terms of the convergent series or smaller than the divergent series, the comparison doesn't apply. Yeah, we have to always make sure, because if this will be this way relation, this is divergent, something that is smaller, we don't know. Could be the finite number, could be divergent, but that's not the conclusion based on that test. Yeah, only this way. And for the convergence, if B sub n is convergent, our A sub n has to be smaller. Then we can conclude convergence. If it's greater, I don't know. We don't know. Okay, that means let's solve a couple of questions. What is helpful to know? Like what we will compare to? Usually the P series is a good, simple, known formula, and we can try to compare. And usually what we will do when we have a rational function, rational expression, rational series, we may only focus on the leading terms of the highest power of the numerator and denominator, simplify, and then we will compare to the P series. Or if something is similar to the geometric series, like we just did the first example, yeah, then we can simplify, compare to the geometric, because geometric is also easy to determine the convergence right away based on the common ratio. Okay, let's try. Determine whether the given series converges or diverges. And we can see rational function. So what I will do, I will copy this fraction to n squared 4n plus 3. They are all positive. And I can keep 5, and I can keep the highest, the leading function. That's what I will try to compare. Let's get the relation. Denominator is bigger on the left-hand side than the whole fraction is smaller. Perfect. It means when I will create the summation for the same number of terms, that sum is also smaller than this one. I can possibly put the constant outside. Then we will see better. That means this relation holds if we add the same number of terms. Yeah. Okay, now we can see P series test. P is 2 greater than 1. This infinite series is convergent. Convergent by P series test. We can use this. And something that is smaller is also convergent. It means our original formula is convergent by direct comparison test. And we directly comparing with, actually, I supposed to say everything, because that 5 and 2 is also part of the relation. Yeah? 5 over 2, and the main formula is 1 over n squared. But the comparison worked. Next one. The same thing. We can take our original formula, all of the terms are positive, and I can keep 2 and 2, actually it's cancel out. I can keep 2 on the top and take the leading term. And this one is even cancel out. And maybe let's speed up. For the same number of terms, when we add them, which fraction is bigger, which fraction is smaller? Actually, let's keep this one for a second. Yeah. Again, we're adding 3, denominator bigger, the whole fraction is smaller. Okay, and this one is 1 over n to the power of 5. 1 over n to the power of 5 is, this series is convergent by P series test. P is 5 greater than 1. Then something, the summation that is smaller, it's also convergent. Convergent, but not by the P series test, by directly comparing, direct comparison test with, and I can even copy this, comparing with that formula. It's important to indicate what we're comparing with. Another exercise, we like exercise. Okay, summation from 3 to infinity, inverse tangent of n, arctangent, over n squared. Okay. Oh, not good color. Let's say, okay, I can keep inverse tangent of n over n squared. I can keep n squared. And now, how can I compare inverse tangent? We know that all of the terms of the inverse tangent, that's arctangent, are smaller, always less than pi. Negative we're not even considering. Let's say this is like a sequence. inverse tangent of 1, inverse tangent of 2, inverse tangent of 3, 4, 5, but all of the terms are always less than pi over 2. Yeah, nice comparison. I basically use that inverse tangent of n is always less than pi over 2. That's also the hint for some comparison. Okay, so this summation, inverse tangent of n over n squared is smaller, this is constant, than this summation. And again, our comparison works. You can see right away, this infinite series is 1 over n squared. P series is convergent by P series test. P is 2 greater than 1. Then our original formula, it is convergent. Because it's smaller, everything what is smaller than the finite number is it's finite number, convergent. Convergent by direct comparison test with, and let's keep that pi over 2, important, 1 over n squared. Starting from 1, okay? Next one. Oh, trigonometric. Sine square of n over n squared. Sine square of n over n squared. I can keep n squared, and sine of n or sine of n squared is never greater than 1, smaller or equal to, because we have the values of sine of n being 1. Perfect comparison. Let's speed up. This inequality works for the same number of terms added, and this is convergent by P series test. P is 2 greater than 1. Then our formula, our infinite series, is also convergent. Convergent by direct comparison test with 1 over n squared with the P series test. Perfect. You will be an expert with the comparison test. Okay, next one. Oh, -1 to the n plus 7 over n to the power of 4. We see -1 to the n, but however, that 7 is making the terms positive. That's why we are not worried for having negative terms, because if we have negative terms, we are not allowed to use comparison test. Okay, I will keep this. I have almost no choice. Or actually, theoretically, you can compare your given formula, given series with anything. If you can explain and prove that everything works, you can compare with anything. Okay, and we may notice this is n to the power of 4. That means probably I would like to say that P is 4 greater than 1. Then infinite series is convergent, yeah, by P series test. But what I can put here to make this inequality smaller. We may find out what is the lowest value. -1 to the n sometimes is +1, sometimes is -1. That means -1 is the smallest value. -1 plus 7 will give us 6. That means this will be less than 6 or equal to 6. But the other value is 8, because if the -1 to the n is +1, 1 plus 7 is 8. But then inequality will be placed the other direction. Okay, okay, and then I can say this, the summation for the same number of terms, the inequality holds. And yeah, that 6 can be placed in front as a constant. This is convergent. Our infinite series is also convergent. Convergent by direct comparison test. Actually, I have all of the convergence. Let me give you this formula. -1 to the n plus 7 over n, because that will be interesting. Yeah, let me just start. Like what we can compare with. I can keep n, and we can see n looks like a harmonic because it's n to the power of 1. That means this will be divergent. Yeah, divergent. Then what I need this. If we would like to claim divergence based on the direct comparison test, I have to have this inequality. That means this expression is greater if, yeah, it's, am I right? Hold on, shall I put, I'm just, okay, this is greater. No, I think that's good that I gave you this one. Wait a second. Is 6 the good number? We need everything smaller. And actually, okay, that means we have to take the maximum number like we did for the sign. Oh, the other way. Because when I put, it's good that I didn't switch, yeah, 6, 2, yes, too excited. Actually, this quantity could be 8, and that's not true. 8 is greater than 6, correct? That means, no, we have to put 8. Then everything is smaller, because when -1 to the n is -1 plus 7, it will be 6. Yeah, this quantity just changed. The top quantity just changed between 6 and 8. And if this is 6, then it's less than 8. Now we can put 6 because it's equal to 6 or greater than 6 if this is 8. Okay, no, 8 here and 6 here, because I'm trying to figure out the inequality. I want this way, because now you can notice I may apply the direct comparison test. If this is divergent series, yeah, it's 6 times the harmonic one, then everything what is bigger is also divergent. Okay, I'm happy that I didn't switch. This one is divergent by direct comparison test, and let's say we're comparing with 6 over n, 6 times harmonic. This one we're comparing with 8 over n to the power of 4, p series, because 8 is the maximum value of this 1 plus 7, everything else is smaller. Yeah, we're not touching denominator, that's we're just looking at the numerator. Now 6, let me just clarify. 6 is lowest value. Everything is equal to 6 or greater than 6. If -1 to the n becomes 1, 8. Okay, 8 and 6. Good that we corrected. Okay, let's see a couple of more and we will be done with this, with direct comparison. Okay, 1 over n, 1 over natural log of n. Okay. Yeah, this one we have to be careful because natural log of n also has negative values. But you can see we're starting from 3. And then when we look at the logarithmic natural log of n, that's the sequence, starting actually from 1 is also not good because ln of 1 is 0, but ln of 2, ln of 3, ln of 4, 5, 6, starting from let's say from 3, yeah, it's definitely actually I can put e, because the value ln of e is 1. Starting from 3, we definitely have positive terms. That's the reason that you can see 3. But it's, yeah, that's fine. We can start from 3. Okay, how can I compare natural log of n? Depends, yeah, depends what relation we need. Sometimes it's good to compare with n and sometimes with maybe just 1, but 1 will be not helpful here. Let's try this, just to comparing with n. Okay, which fraction is greater? Natural log, actually I have the graph, I can use it. Natural log of n looks like this, and function n will look like just what, y equals to x, y equals to n. And we may notice this is definitely bigger. That means n is greater than ln of n. Now, if the denominator is greater, the whole fraction is smaller. Makes sense? Because n is greater than ln of n. If the denominator is greater, the whole fraction is smaller. Perfect. And what we have? For the same number of terms, that summation, starting from 3, will be greater than this summation. Let's also say. And this is harmonic series divergent. Everything what is greater than infinity, than divergent, we can claim divergence. Divergent by direct comparison test with beautiful harmonic series 1/n3. Okay. Okay, let's see, because we may, I have also this one. The same thing, I just put 3 because natural log of n is, we need a positive, we need a positive terms. We don't have to read this instruction. Okay, let's try this one. What we can do for this one, natural log of n over n. Okay, what we can try? We can try n, and now I can maybe put 1. I'm trying to compare natural log of n with 1. Of course, natural log of n is greater than 1. When we draw natural log of n, ln of n, and 1 is just the horizontal constant function. And natural log of n is greater than 1 starting from e, which the first integer after e is 3. That's the reason that we have 3. Then this inequality works. And when I add the summation, let me put natural log of is greater for all n greater than or equal to 3. Okay, so this summation, not the same number of terms of this sum, it's greater than the same number of terms of this sum. And this one is divergent. And everything what is bigger, our original formula is greater than infinity. It's also divergent. Divergent by direct comparison test with harmonic, but starting from 3. It's fine. We can skip a couple of time items. Okay, and let's do maybe one more and we will finish. But what you have to check, my one extra video, because we do have another version of comparison test, not direct comparison, but it's called limit comparison test. Okay, but we will do not this one you can try, this one you can try. This one is the list of like potential possibilities of comparison. We can see when we have this geometric similar formula, we can just take these leading terms and create the geometric. For the rational function, leading terms. For arctangent, pi over 2. Sine of n can be compared with 1. Cosine of n also. E to the power of 1 over n is always greater than 1. This one, we did -1 with the 7. Depends what we need. Yes, greater or smaller. Logarithmic function. If we need the inequality this way, we can compare ln of n with 1 or ln of n with n. And actually, we can compare with natural logarithmic function with any power function. Any power function will be always greater than natural log function. Yeah, and even if I will take another like power of both sides, this is still greater. If I flip the fraction, this side is greater. That's it. Let's finalize this session with this one. Yeah, let's do this one, because this one is interesting. You have to figure out that power. Determine whether the given series converges or diverges. Natural log of n to the power of 100 over n to the power of 1.1. Okay, interesting. Probably I don't know right away, but I can start slowly. If I type something, okay, I didn't, which is excellent. Let's start with natural log of n being less than n. Okay, then natural log of n is still less than n to the power of any number, yeah, because I will try to use the p series. Like, how can I compare? Okay, now I can take natural log of n to the power of 100, because we have that 100, and n to the power of p, 200. Okay, I can also take natural log of n to the power of 100 and divide by 1.1. What I'm trying to do on the left-hand side, create our formula. Okay, and n to the power of 100, still inequality works. Yeah, actually, let's say 100p. Yeah, because when we have p and 100, we can multiply 100p. Okay. Now, this is our formula. That means I don't even have to repeat this formula. Now, let's work on this side. When we have n and n, and we dividing, we can subtract these exponents. Yeah. Now, I can flip the number, my unexpected line, n to the power, because this is n to the power of that number, I can say 1 over n to the power of negative, and I can switch the signs, applying negative. Perfect. It means now this fraction on the right-hand side is smaller than our formula. Okay. If it's smaller, I want this to be convergent, because then I can use comparison. I mean, this formula, right? This formula, the sum, of course, when we add the summation, I can maybe now rewrite here. Our original series is probably convergent because it's less than 1 over n to the power of 1.1 minus 100p. Yeah. But this is convergent if this quantity is greater than 1. 1.1 minus 100p must be greater than 1. Yeah? Like the whole quantity, I could use different letter than p, but the whole quantity is like a p-value for the p series, 1 over n to the power of that cloud, that p. This has to be greater than 1 for convergence. Then if this is greater than 1, this sum, that side is convergent, okay, convergent, and then we can claim that this is also convergent. Convergent by direct comparison test, and we comparing, but let's find out the value of p actually. Negative 100p, and we can, what we can do, we can subtract 1.1, it will be 1.1, and then we will divide 1.1. No, something is wrong, negative over negative will be positive. Dividing by negative number, we're switching the inequality. Okay, that means p is basically number less than 0.01, am I right? 100, 1, 2, yes. I mean, we may pick any value, small, right? Small small value, any value less than 0.001. We can even pick 0. And then if you will, then we can compare, like if this will be 0, we can see we will have n to the power of 1.1, which we can also do this, no problem at all, okay? But we can see any value of p less than 0.001 substituted here will give us the convergent series. And if it is convergent with the p being any being less than 0.005, then this is convergent. Our green box is less than finite number, then it's definitely convergent by direct comparison test, and we comparing with 1/n to the power of 1.1 minus 100p, and we can pick any. So theoretically, everybody can have different answer. You can pick any value of p. 0, any negative, because negative times negative 100 will be positive, this will be big. And if this exponent is, this power is big, the p-series test will, okay? But p could be from this, okay? That's nice general solution. Okay, let's finish. Make sure that you know all of these problems, practice the comparison, because it's nice and simple if we have enough practice. Yeah? And check the last practice problems and actually the next test, which is the limit comparison test. Thank you.